Okay, so question 11. Now, this looks a lot more intimidating than it is. You just have to think about this in terms of being solutions of a unit circle. So the first thing we're going to do is consider the complex number w as shown in the plane. So we're looking at this coordinate over here. Now, next thing we're going to do is determine w, expressing your answer in the form of r cis theta. Now, one other thing that's important to note in this question is it says that it's from the unit circle. Now, if we're talking about the unit circle, then the unit circle standardly has a radius of 1, meaning that to determine the complex number w in this case, all I need to do is determine the modulus of the argument, which is going to be this. So I would square and square root 1, which will just give me 1. And then the next thing I'm going to do is determine the argument to get me to that position over here. So the angle that's going to be going into this, if I think about breaking this up like that, I've got 3 equal sections, so I can do pi over 3, and this is the second section will get me to that spot. So all I have to do now is to state this in the form of r cis theta. So that coordinate of w is equal to 1 cis 2 pi on 3. And that's it. If we want to make it a little bit easier, all we have to do is write it without the 1 in front, because we know that this simplifies into just being cis 2 pi on 3. So pretty standard for the first one. Next thing we're going to do is we're going to convert w into Cartesian form. Now, when we convert into Cartesian form, it means that we're looking to get it in the form of a plus bi. So it'll have the real and the imaginary component. That way we could plot it on a Cartesian plane or the arcing plane. So all I have to do this is to break our polar form from the top here, the r cis theta, into being its cos and sine. Now, the hint to remembering that is in the word here, because cis starts with cos. So w is equal to cos 2 pi on 3, brackets, plus sine 2 pi on 3, and the sine part is your imaginary component. Now I can start looking at my exact values to break these sections down. So cos of 2 pi on 3 is over here, meaning that it is a negative value for cos. And that's 60 degrees, so if you use your hand trick, it's going to be root 1 on 2. Minus 1 on 2. And then for sine, it'll be positive because that's the quadrant that it's in, and its coordinate is going to be still 60 degrees, so it'll be root 3 on 2i. So that's the Cartesian form. Okay, each vertex of the hexagon has a solution of an equation in the form of Zn equals a, where Z is elements of the complex system. If you'd like to get further context about these questions, you can go to chapter 5.6 in the Jack Plus textbook. And the question that I looked at to help me piece this together was looking at example 19. So all I have to do here, there is going to be 6 solutions because we could see above that the hexagon had 6 points on the unit circle. So n is going to be equal to 6. And then a is going to be equal to 1 because of the first coordinate of the unit circle. So if we go back up here and we look at this first coordinate here, when we go through and we find all of those different roots of it, we're looking for this coordinate, that one, that one, that one, that one. So this as a coordinate, this point right here is 1 in the real axis plus 0 in the imaginary axis. So that will give me my first point. So come back down here. Next thing we're going to do is we're going to verify that W satisfies this for our equation that we found before. So we're going to need to find the roots of unity to do this. So our first step is going to be I'm going to use our cis form to help us out. So we're going to let k equal 0, which means that we'll be finding our first solution. This will allow us to verify that our first thing is going to be correct. So it'll be cis, or should be root r, n like that, and then 2 pi times your k value over your n value. So when I substitute these values into this, I'm going to get 6 root 1, which will just simplify to 1, cis 2 pi times 0 over 6. So that's just going to be cis of 0, which will in fact give me cos of 0 plus sine of 0i. Now if I break them down, that's 1 plus 0i. So I know that that is correct for the first solution that we found. Now I could go through and verify this for the next ones. I could do this for the whole way around the circle. But it's only asking me to verify w. So that means that if k is 0 and z is 1, and we want z to be our third solution, that means that we really just want to substitute in k equals 2. So to find that, this part simplifies to 1, so it's 1 cis 2 pi, k in this case is going to be 2 over 6, so that's going to be cis 2 pi on, oh, not 2 pi, wait, cancel you, you're a 3 down here, yeah, so 2 pi on 3, close bracket. That means that now I can break it down into its cos component and its sine component. Oh, look at this. She's looking familiar. I've seen you before. So 2 pi on 3i. And then this is what we found up there. So now we know that this is going to be the same. So cos of 2 pi on 3 is going to work out to be negative a half plus root 3 on 2i. And let's just go back and check. Yes, that's correct. Okay, perfect.